All right, folks, so let's get started. I saw half of you in lab yesterday. Oh, it was so great seeing you guys in lab. I just wanted to point out that, remember, I went to graduate school here, so I used to be a TA, like your TA that you have, that used to be me, just a couple years ago, okay? Yeah, that used to be me. So it was great talking to you guys in lab. You guys were so excited to describe to me what you were doing, because I had no idea. I've never done this lab before, the copper cycle lab. So it was great to hear you guys try to explain what you were doing. So remember, lab really elevates our understanding of things. So with that copper cycle lab, it really focuses on the activity series, so chapter 4 stuff. Really, when you're inspecting your observations and reflecting on your post-lab things, really think about what is in the test tube. Right, when you threw in your like copper oxide, the acid, and then like a piece of metal, really think about all the species that are in that solution and what can possibly react via the activity series. Remember, the metal, the neutral metal, needs to be higher on the activity series than the cation, and that should be lower, and then that is a spontaneous reaction. So really think deeply about what is in that test tube. So that's my tip for you. Right, okay, so we left off talking about the photoelectric effect. So this was Albert Einstein's Nobel Prize worthy experiment, all right? It proved that photons, or light, is a wave. That's what we knew through classical physics, but it also behaves as a particle. And I'll show the demo. But on the topic of the Nobel Prize, so I'll prove to you, yeah, so that's David Macmillan, that he won the Nobel Prize in 2021. Yes, right, so here's the announcement, so that's him. Right, so that was in 2021, so just a couple months ago. And so here's my blurb about him, because I invited him. I was the president of the Chem Talks. It was like a graduate student organization, and we bring notable chemists in. And so in 2007, I brought him here, and he just talked across the hallway. Right, that's where he gave his talk, just across the hallway in McPherson something. All right, and then yeah, there's me giving him an award. All right, so basically, that's essentially a Nobel Prize, right? Right? Okay, and there's my BFF, Shelby. She's a chemist too. She makes a ton of money at Intel now. So that's what chemists can do. You can teach, work at Intel, things like that. All right, so that's just my little blurb about Nobel Prizes. And we're going to be talking about a lot of Nobel Prizes in this chapter. So let me just kind of recap. Why we're talking about light, and kind of reference ourselves here. So light, we talked about a wave as having wave properties, where we use wavelength and frequency. We can interchange those units, right, of wavelength and frequency. Now with this equation, E equals hc over lambda, or E equals h wavelength, this is the energy of one photon. So we're treating light more like a particle now, that a single packet of light, it doesn't just propagate infinitely through space. It can we can count them, all right, like particles. And so this equation tells us the energy of one photon. And typical visible light has a very, very low amount of energy, because we see here Planck's constant is a really small number. All right, so visible light is somewhere to the times 10 to the negative 19 joules per photon. So this equation definitely, I'm not sure if you're given it, but definitely memorize this, is to calculate the energy of one photon. All right, and so Albert Einstein's experiment, the photoelectric effect, it really proved to us that light can behave as a photon, and I can kind of prove it to you here with the demonstration, or in that demo. And so kind of just keep in mind here, the way he was able to kind of come to the conclusion that photons, or light, behaves like a particle, it's through the idea of conservation of energy, all right? The whole idea of the photoelectric effect is that the incoming light had to have a certain amount of energy in order for electrons to be ejected from the metal surface. That is the work function of the metal. It's metal specific. So it's like the idea, we have specific heats of metal. Every metal has a specific work function, a specific minimum energy for electrons to be ejected. That's what this I with the belt is. That's the work function of the metal. So this equation basically tells us everything that we need. that the energy of the incoming photon equals the work function of the metal plus any leftover kinetic energy. That's what's going to go to the electron. And we kind of saw that in the simulation video thing, right? So here I have, okay, no, so it works. So this is the photoelectric effect, all right? So this is a piece of sodium metal. That's what's kind of on these anodes here. I have the intensity really high, but the wavelength of light is within the IR region. So IR light versus like UV light, is IR lower energy or higher energy? Lower energy. So what we see right now is I've cranked up the IR light, but no electrons are being ejected. And I can change the intensity, right? And electrons, electrons still are not ejected, even if I crank up the intensity. But in order to get electrons to become ejected, I have to start changing the wavelength of light. When I change the wavelength of light, I change the energy of the photon. So we get to a certain point where electrons are now ejected from the metal surface. So we see it's around 500 nanometers this happens. So I can change the intensity, and that just changes the number of photons that come out. All right? But then what did we observe last time? That if I continue to shorten the wavelength, I'm continuing to increase the energy. So I'm going to change the wavelength now. So what happens when I change the wavelength to become really, really short? The electrons that are ejected are what? Going faster. So if they're going faster, do they have high kinetic energy or low kinetic energy? High kinetic energy. Very good. So, and what we see here is if we change the intensity of these fast-moving ejected electrons, are they still going fast? Yes, they're just not as many of them. So see how intensity is not, the effects here are different than changing the energy of the incoming light for the photoelectric effect. So this is sodium. So here we can do another, metal. So this is copper. So every element has a different work function. So the eye with the belt. So this is copper. And so we can find where the minimum energy is or the minimum wavelength is for copper. It's going to be somewhere else. All right, so it's a little bit higher energy than, okay, so there. So somewhere in the UV region, that is where electrons start to be ejected for copper. Yeah?
So for the equation that you gave us, which number from the thing?
I'm going to go back to that, all right? Yeah. Yes, okay, so keep all those ideas in mind here. So yes, so let's go back to that equation that I showed, and I'll show you that everything that I said is actually within this equation, all right? So energy of the photon, we know that that's inversely proportional to wavelength of light. The shorter the wavelength, the higher the energy of the photon that comes in here. So let's pretend, I'm going to just make up numbers right now. The work function of our metal, so the minimum energy, let's say it's just 1 joule. Okay, just 1 joule. Pretend that we send a photon with an energy of 2 joules. Right? What must the kinetic energy of the electron be? 1 joule, right? And then from there, if we know that the kinetic energy is 1 joule, we can say that what's the equation for kinetic energy? 1/2 mv squared. So we can then calculate velocity, right? If we know what that leftover energy is. Okay, so let's pretend instead of 2 joules for the energy of the photon, let's pretend we send 3 joules of energy to the metal surface. The work function stays the same, right? That the amount of energy to release or eject an electron, it's still 1 joule. So all that extra energy goes where? To the kinetic energy, right? So kinetic energy, instead of having 1 joule of leftover energy, there's 2 joules of leftover energy. That's exactly what we saw, right? That the more energy of the incoming photons, the faster the ejected electrons were. All right, and this is going to blow your mind. What happens when we lengthen? We lengthen the wavelength, the energy goes down, right? So let's pretend we are not at the work function of the metal. All right, so let's pretend we send half a joule of energy of a photon. Let's just pretend that. Okay, but the work function is still 1 joule. what is the value of kinetic energy? Negative 0.5. So remember, I'm just making up numbers, joules, okay? Negative. So in this example, I'm saying that the energy of the photon is less, the energy of the incoming photon is less than the work function. The wavelength's longer. So I just said that the kinetic energy of the electron is negative half. If we set that equal to equals 1/2 mv squared, can we solve for v? You can? What's the square root of a negative number? It's an imaginary number, right? So does the electron have a velocity? No, because what happens when the wavelength or the energy of the photon is too low and not above the work function of the metal? Nothing is ejected. So if we kind of inspect this equation, when we see that the energy of the photon is too low, that we get a square root of a negative number, an imaginary velocity, nothing is ejected. Does that blow our minds? Yeah, so it proves exactly what we observed here, and that's why this is Nobel Prize worthy. All right, that, this equation, energy equals, potential energy plus kinetic energy, that's kind of a big thing that we talk about with particles. And we're treating light just like we were treating everything else in chapters, within thermodynamics with actual matter. And I think that's like a beautiful thing. And that's what gets me jazzed about chemistry. So did we answer these questions? If a lot of photons strike the metal, increase the intensity, a lot of electrons are also ejected. They all will have the same kinetic energy because we're just changing intensity, we're not changing energy. If higher energy photons hit the metal surface above the work function, we're essentially, giving all that leftover energy to the ejected electrons so they move faster. And so that's what we kind of see in this equation, and also this graph shows the exact same thing as well. All right, so do we feel good about the photoelectric effect, why it's Nobel Prize worthy? Yeah.
Calculate the energy of the photon or the speed of the electron. How do we get the number originally? Is there an equation that relates wavelength to energy of the...
Oh yeah, so is there an equation we can relate wavelength of light to energy of that light? Do we know what equation that is? I just talked about it previously on the slide before. Yeah, it's this. So I just made up numbers here, but it's this equation with Planck's constant: E equals h frequency, or E equals hc over lambda. So the left side of that equation, E photon, that energy is coming from this equation right here. So we can calculate the energy of one photon. Does that make sense? Okay, so let's do a calculation now. Light is a particle, so we can count them like particles. All right, we can calculate the energy of one photon using E equals hc over lambda. So since light is a particle, we can count a mole's worth of light or of photons. So let's walk through this calculation, because sometimes when we come across light energy, it's not expressed as energy of one photon. Sometimes it's expressed as energy of a mole's worth of photons, and so I'll show you how we get those calculations here. So this question is asking, what is the energy of a mole's worth of photons with a wavelength of 204 nanometers? So 204 nanometers, is that frequency or wavelength? What? Wavelength. It's wavelength. It's a length. 204 nanometers is a length, it's like a meter, so that's a length. So this is wavelength. So if we look at our equations here, E equals h frequency. If we kind of combine that with our idea of how frequency and wavelength are related, we get another equation, E equals hc over wavelength. Both of these equations are the exact same. All right, it's just, am I given frequency or am I given wavelength to use? So we want to use the second equation here because we're given wavelength. But remember, when we plug into this equation, we get the energy of what? one photon, just one of them, like picking up one little photon. So when we plug this number in, 204 nanometers is also equal to 204 times 10 to the negative 9 meters. So that's like a little trick for you, because nano means to the negative 9. I'm just going to plug that value into our E equals hc over lambda equation. So h is 6.626 times 10 to the negative 34 joule second, times c, or speed of light, so 3.00 times 10 to the 8 meters per second, over wavelength, so 204 times 10 to the negative 9 meters. So just canceling out units to show you that it all works out. Seconds in the numerators cancel, because we have one on the top, one kind of on the bottom there, and then our meters also cancel. So we're left with the unit of joules. So, and that's energy, so that's good. So plug that into your calculator, and you get 9.744 times 10 to the negative 19 joules. So just to kind of like reinforce the idea, that energy, so this is energy, but energy of what? One photon of 204 nanometers, just one photon. So we want the energy of a mole's worth of photons. So I like to think to myself, okay, this is a joule, this is one photon. So if I have a mole's worth, I have 6.022 times 10 to the 23 photons. Right? So I'm going to multiply this number by 6.022 times 10 to the 23 photons is 1 mole of photons. All right? So there we go. And so if we check our units here, photons cancel. So now I'm in the unit of joules per moles of photon. Is that what I want? Is that what I want here? No. What does the question ask for? In the unit of kilojoules per mole. So one more step there. So be very cognizant of what the question's asking for. We're in the unit of kilojoules per mole, or sorry, joules per mole. So we need to just divide by 1,000 here to get kilojoules. All right, and so our answer to, I think, 3 sig figs, yeah, because wavelength is 3, is 587 kilojoules per mole. So the two numbers to really kind of look at here is the energy of a mole's worth of photons. Typically, it's expressed in kilojoules. And then we also see here the energy of one photon. And so we should always be able to convert between those two numbers. That the energy of one photon is given to us by the E equals hc over lambda, or E equals h frequency. Okay, yeah. Did you get a different number? Okay. 204 number. I mean, we have to use the 204 number to get the energy of one photon, so we have to do that. I don't have an equation to go straight to a mole's worth of photon. I mean, or you could just think, okay, multiply that E number we just got by Avogadro's number. Okay, so just know that that E equation with Planck's constant is the energy of one photon. All right, and the reason we can say this is because of Einstein, because he proved that light can behave as a particle, not just a wave. All right, okay, how do we feel about this? Good. Okay, we can put our calculators away for a while. All right, that was a joke, kind of, but yeah, okay, all right, so I'm gonna keep going. About other Nobel Prize worthy experiments. Okay, so we're gonna get into the meat and bones of this, this chapter, so buckle up. So we learned about light. We can see light. Yes, you nod with me. We see electrons? No. So where a lot of these Nobel Prizes came from is relating observations we can make, and they typically involve light because we can see light, and relating that to the structure of an electron. We can't, or the structure of an atom relating to their electrons. We can't see individual atoms. We can't see electrons, but what these scientists did is took observations that they made and related that to some model that was able to fully explain the purpose of electrons, and that's what made it Nobel Prize worthy, really. So the Bohr model is the first model that gets us part of the way there. The Bohr model is actually not correct, but the Bohr model kind of lays the foundation for the rest of the, more accurate models, such as the Schrödinger equation. It kind of lays the foundation, and it actually explains the hydrogen atom pretty well, even though it's wrong a little bit. All right, so just keep that in mind. So I'll talk about the tenets of the Bohr model coming up. So just to recall from a little bit from chapter 2, right, where in chapter 2 we talked about specifically subatomic particles. Right, electrons, nucleus that has the protons and neutrons, right? And so we talked about, 3 big experiments that differentiated the different subatomic particles. Those are the first 3 experiments up there, right? We went from the Dalton model, then we were like, oh wait, electrons exist, so that's the plum pudding model. And then Rutherford was like, hey, there's a dense nucleus because alpha particles were deflected. That's the nuclear model. All right, that's where we stopped in chapter 2. Rutherford got a Nobel Prize too, but it's for radioactivity, not for his model. Now this is where we are. We're at the Bohr model now. So it looks similar to the Rutherford model that we have a nucleus and we have electrons around it. But what makes it different is that we have, you might have seen, nuclear models like this. We have these specific orbits around the atom. And so I'll show you where those orbits come from. They're coming from energy levels of the electron versus, and so the Bohr model does get a Nobel Prize. And then finally, just, a decade later, this is the real model of the electron. Okay, so we will learn this. And this is the Schrödinger model. So just a couple years went by and we kind of took this huge leap forward in understanding what atoms look like. So again, we can't see electrons, but we can see light. So what's really interesting about hydrogen is, and light in general. So when we think about white light in this room, white light is actually composed of all colors of the rainbow. You put white light through a prism, it disperses, right? Like the Pink Floyd album or whatever, right? That's the rainbow. But what's different about hydrogen, kind of like a neon tube sign, where you have an element filled up in a gas tube and you send electricity through it and you see light coming off. We can do that with hydrogen instead of neon. So that's what they did back, in the early 1900s. They put hydrogen in a tube, sent a bunch of electricity through it. They saw light come off, but the result when they sent that light through a prism, it wasn't a continuous rainbow spectrum like we see with white light. They saw specific lines. And just imagine, and you're in the 1900s and you saw something like that. You saw specific lines. When all the light that we interact with in our everyday life is continuous. It's always all the colors of the rainbow, always. But with hydrogen, they saw specific lines. So this is what we call the line spectra of hydrogen. All elements have very specific line spectrum. So this is the continuous rainbow color, the Pink Floyd album. But when we put elements in these discharge tubes, light comes off, but it's lines of very specific wavelengths. So that's what you see here. So this is hydrogen. There's 4 specific lines within the visible region that they saw. Okay, and to them back then, it blew their mind. All right, and what is Nobel Prize worthy here is that Bohr was able to figure out what the meaning behind these lines. And that's kind of the amazing thing here. All right, so these lines that you see from the hydrogen discharge tube, the cool thing is that every element, when you put it into a tube, like a neon sign, just the same, a discharge tube, they all have unique signatures. All of them have very unique lines. So that's pretty cool in that it's a way to identify elements. So a cool thing, one of the only elements that was discovered elsewhere, not on Earth first, was helium. Helium was actually discovered on the sun first. It was actually through its line spectra. They observed the helium line spectra from the sun before they found helium on Earth, which I think is kind of cool. Because what is like the Greek god for the sun? Helios. And that's my cat's name. It's my cat's name. But I call her Babes, or Bean. I usually call her Bean. So anyway. Okay, so every element has a unique spectrum. So this is neon, the spectrum from neon. So obviously when we look at a neon sign, we don't see those individual lines. We see all the lines at the same time, right? A neon sign is typically really red. So what you're seeing is mostly the red lines. So in order to see all of the actual individual lines, you have to send that light through a prism in order to separate it. And I think you'll do that in a lab. I don't know which one. The one about hydrogen. You will do that in lab. We have discharge tubes that you get to look at. All right, okay. So the Bohr model isn't coming up yet. So the big idea with the Bohr model is that Bohr took the idea of these lines, fit it to a model that made sense and described electrons and the energies of these lines perfectly. The thing is that a scientist before him, Rydberg, came up with an equation to describe those 4 visible lines that we see for hydrogen. So this is the Rydberg equation, and it was developed in 1888, so like really early. So really early that they developed this. But the thing is that this equation, and why Rydberg did not get the Nobel Prize, is because it had no meaning. He just kind of played around with numbers until he was able to predict all 4 of those lines on the hydrogen line spectrum. So he saw that, hey, if he played around with numbers a lot and took the inverse of integers squared and subtracted them from one another, and then multiplied by a constant that he named after himself, he was able to predict the hydrogen lines. All right, so that is not Nobel Prize worthy when it's just an equation, because he had no explanation for it. He just kind of played around with numbers until it fit. So we have this equation now that kind of gives us a glimpse into what the Bohr model is. The subtlety here is what he puts under those numerator, or the denominators here, integers, that in order to have those lines show up at the right wavelengths and the right energies, he had to take the inverse of integers squared. So these integers will have meaning in a little bit. They're related to energy levels. And so this equation only relates to the hydrogen atom. Yeah?
So if you try to predict where they are, does that mean lines spectra could move based on sample size?
No. So these line spectra, it's an intrinsic property, so it's based upon the identity that it's hydrogen.
Why can you predict it?
What?
Why can you predict it then if you already know what it's going to be?
Oh, so it's like the whole idea, this is science. It's like we see something, they show up in a place, but when we can fit a mathematical model to it, that's where a lot of like learning and a lot of understanding comes from, right? Like we can throw a ball up into the air. It has high kinetic energy, lower kinetic energy until it kind of turns back around and drops back down. We can use classical physics like potential energy, kinetic energy to describe that. So really what science is finding mathematical models and fitting it to our observations around us. So if you're a science person and that like totally interests you, then you pick the right fields, because we use numbers to explain everything. But what makes it Nobel Prize worthy is that those numbers and that equation has meaning within a model that chemists and scientists recognize is correct. Does that make sense? Yeah. So he essentially, played around with numbers until it fit. And that's what this equation is. Yeah.
So like for the line spectrum, so carbon and nitrogen, right?
Mm-hmm.
Plus 1 proton. When we saw the line spectrum of helium, did we know it was that element with 2 protons? Or like, did we not know where it would go?
We did not know at the time.
How did we?
We just knew it was a different element.
Okay. So like you couldn't predict the next line pattern based on the line pattern of the list?
These scientists could not. No.
Can we now?
Can we now? Yes, because we have supercomputers to solve the Schrodinger equation.
So we don't have to do that on the test?
No, you don't have to do that on the test. Okay. All right. So let me put this story together. All right, okay, finally we can talk about the Bohr model, but let me like reference you. Okay, we started with the nuclear model, right? Rutherford, we have a nucleus. We have electrons, they're on the outside. And what we're gonna learn here and for the next like 5 chapters is that electrons are frickin' important. They predict everything. It's electrons that predict reactivity of elements. All right, we have this idea of the Rydberg equation, all right? Rydberg, he came up with an equation. He saw that, hey, if we play around with these integer values, we can recreate the line spectrum we see for hydrogen, but he didn't have any meaning. He didn't know what those integers meant. That's why it's not Nobel Prize worthy. Sorry, I keep dissing him. Yeah, sorry, Rydberg. And now we have this idea of, hey, energy is quantized. We can calculate the energy of 1 photon of light. So I'm going to put all these ideas together, and these are the 3 tenets of the Bohr model. They are mostly correct, and they get us a big step forward to the Schrodinger model, but it isn't quite correct. But typically in high school, this is the model that you learn, and then like you stop here. All right, so I'm going to tell you that this model is actually wrong. All right, let's go. So these are the 3 tenets to his theory. I'm going to go into all of them in detail. Okay, so the big idea, and this is kind of a glimpse to the Bohr model like picture I saw with the electrons kind of in those orbits, is that electrons can only exist in orbits. So what does this say? Only orbits of a certain radii correspond to certain specific energies and are permitted for an electron to reside in a hydrogen atom. So typically in this part, when we talk about energy levels of a hydrogen atom, we talk about rungs on a ladder, that an electron can only exist in certain integer energy levels. So this is where the integer value thing comes in from the Rydberg equation. That an electron can only be in either n equals 1, n equals 2, n equals 3. It can't exist in between levels. It's like rungs on a ladder. So just to kind of give some definitions, the lowest energy rung on the ladder we call n equals 1. So n equals 0 does not exist. We start at n equals 1. And we call this the ground state. So you can kind of think of this as the bottom rung of your ladder. Any energy level above that, so 2 and above, those are we call excited states. That when an electron is in those higher states, it's excited, it's at a more positive energy value, a higher potential energy. All right? And so what these numbers have meaning, they tell us the distance away that electron is from the nucleus. So n equals 1 is the closest. Oh, this should say electron, right? Yeah, that should say electron, right? Electrons orbit around the nucleus. So n equals 1 is the closest, and then n equals 2, 3, 4, 5, etc., all the way out from the nucleus. Right, so n equals 1, your ground state is closest to the nucleus. So what Bohr was able to do was kind of mess with the Rydberg equation and come up with an equation to estimate the absolute energy levels of each of the energy, let me repeat that. Bohr was able to predict the energy level for each n value of an electron. And it looks very similar to the Rydberg equation, because see how we have that n squared value in the denominator? It's very similar. But this equation is different than the Rydberg equation. This equation predicts the absolute energy in joules for any electron in a certain n energy level. So keep that in mind. But this is kind of giving us a glimpse into the idea of quantum numbers, where we have integer values, they can only be like 1, 2, 3, etc. And this whole idea that energy is quantized, where we can have electrons move between energy levels. All right, so that's the first one. Electrons can only exist in integer value energy levels. They're kind of think of it as rungs on a ladder. So you can see as n increases, if you climb up this ladder, kind of like your stability decreases, right? So your energy, your total energy increases as you increase your n value, as you get further from the ground or further from the nucleus. Okay. All right. So yeah, actually, let's talk about and connect this to the idea of chapter 5 and potential energy. So this is what the energy levels look like for an electron on a hydrogen atom. So the subtleties here is that we don't just put the energy levels like 1, 2, 3, 4, 5, like all equally spaced. What's really important here is that the energy levels actually converge. They get closer and closer together as you increase your n value. So here's n equals 1. This is n equals 2. So that's the biggest jump. N equals 3, 4, 5. They get closer together. That's a really important detail here. And so we see that the energy increases, becomes more kind of unstable, you can think. So let's relate this back to chapter 5 terms. So you see here the energies on this side, they're all negative. They're all negative. Why are they negative? Why are these energies negative? So I'm going to draw what everyone loves. Okay, our potential energy diagram. The top of this graph is what type of interaction? Repulsion or attraction? Repulsion. The bottom is what? Attractions. So we have an electron, and it's orbiting a nucleus. What is the charge of a nucleus? Positive. So an electron is negative, a nucleus is positive. So are we operating in repulsions or attractions? Attraction. So that's why all these values are negative, okay? Attractions. All right, so we got that. As n increases, how does the distance from the electron from the nucleus change? As n increases. Does it get closer to the nucleus or does it get further away from the nucleus? Further away. So what we see, if we go back to our energy diagram here, as n increases, we say d increases, right? N increases, distance increases. So what happens? Potential energy increases, it becomes less negative or it becomes more positive in this case. So we can see that higher n values are, I guess I want to say like less stable. They have more energy, so to say, within there. All right, how does the potential energy change as distance between attracted particles changes? So the same idea here. As n increases, d increases, so our potential energy increases. It's no longer stabilized. That's why we say n equals 0 is the most stable state. It's the ground state because it's the most negative the most negative potential energy. All right, what is the energy of an electron at n equals infinity? Does anyone want to guess? Okay, n equals infinity. What is d? Infinity. So what's the attraction when two particles are infinitely far apart? 0, 0. So our potential energy when you completely separate an electron from its nucleus is 0. Boop. Potential energy equals 0. Very good. All right. You tell me. You tell me. As you're saying, as n increases, distance increases. So are we going up the curve or down the curve? So is potential energy increasing or decreasing? Increasing. Very good. All right. So orbits, blah, blah, blah. There we go. So let's go on to the second tenet. All right. So here, an electron is permitted orbit. In a permitted orbit is in an allowed energy state. An electron in an allowed energy state does not radiate energy, therefore does not spiral into the nucleus. So this second tenet is basically just saying that electrons are only allowed in n energy levels because they are not making transitions, they are not giving off or absorbing energy. So I like to pose this analogy, I guess. Right? So basically, Bohr is saying, hey, electrons can exist in these energy levels, but only in those energy levels. Okay? So imagine me standing on the ground. If I'm standing on the ground, am I radiating any energy? No, I'm not moving, right? But what if I, someone just like picks me up 10 feet off the ground and lets go? What's going to happen? I'm going to crash to the ground, right? Yeah. So the idea is like, why don't electrons do that, right? I think this is a really valid concern here. Electrons are negatively charged. Nuclei are positively charged. Why doesn't the electron and nucleus just crash together? Are you sitting there thinking about that out there? Yeah. So here, this is my reasoning to answer that. So yeah, electrons and nuclei, they're oppositely charged. They should, like magnets, just crash into each other. But the Bohr model explains why it doesn't. And it's the idea of energy levels and the ladder, so to speak. So my analogy here, where's my analogy here? All right, yeah, so I'm on the ground, I'm not radiating any energy. But if you pick me up 10 feet off the ground and there's nothing below me, I'm just gonna drop to the ground, I'm gonna radiate energy in that case. But if you pick me up and there's like a ladder there, all right, and you pick me up to a higher state, if you increase my distance from the ground or from the nucleus and there's a ladder there, will I fall? No. So it's the same idea with an electron. Now that we have this ladder or these energy levels, the electrons will stay in place in those energy levels as long as they don't move between energy levels. Okay? Does that kind of make sense? Yeah, so this is why electrons and nuclei don't just crush together. Okay. All right, so let's think about, well, now how is light related to all of this? So light is so we know where electrons live now. They live in these rungs, they live in certain energy levels. All right, so how is light involved? Light is involved when electrons move between energy levels. So when they're just in one energy level, like n equals 2, and they're just chilling there, they don't radiate they don't emit any photons, they don't absorb any photons. It's only when they move between energy levels, like n equals 1, 2, 3, whatever, do they either absorb or emit energy. It's the same idea with a ladder. If I'm sitting on the third rung of a ladder and I'm just standing there, I'm not inputting any energy to do anything. But once I want to start moving, like going up the ladder or going down the ladder, then I do have to involve energy somehow. So we see light when electrons move between energy levels, all right? Yeah, so what was observed here is when we take a hydrogen atom and we shine white light at it, certain wavelengths of light was absorbed by the hydrogen atom. All right, so this is, we call the absorption spectrum of hydrogen. So only very certain wavelengths of light was absorbed. So those wavelengths that were absorbed, it was related to the energy difference of two different energy levels. So this gives us no, not quite, the next equation that we get. So yeah, the idea here is that only transitions result in light. Light either being emitted or absorbed. And what's interesting here is that the light that's either emitted or absorbed, we can calculate the energy for those photons that are involved. E equals hc over lambda. That E is related to the energy differences between energy levels that we talked about before. So that's kind of the beauty of this and why the Nobel Prize Committee recognized it. So recall, transitions are what result in light being involved in with our absorption or emission spectra of a hydrogen atom. So let's kind of think of thermodynamically what's happening. If an electron absorbs energy and that electron is promoted to a higher energy level, right? So the transition here is n is increasing. So I want us to kind of think about this. So n is increasing. So we're like increasing. So like, for example, we're sending an electron from 1 to 2, for example. What is the sign of the change in energy of the atom? Is it positive or negative? If we're putting energy into the atom, into the electron, positive. It is positive, yes. So in this case, electrons are being absorbed. That's the key thing here. Electrons are being absorbed. Okay. So on this picture, what you see is the blue line. An electron's going from n equals 1 to n equals 2. Energy, the photon energy is being absorbed into the system in this case. So it doesn't result in the discharge tubes that we're seeing just yet. What we actually see, what we observe, is emission of light, and that's this other way. When an electron falls back down to a lower n value, it actually releases that extra energy. So here, the transition involved here is n is decreasing. So for example, a electron could be on energy level 2 and go to 1. And in that case, that's this red line, that we have an electron here and it falls to a lower energy level. All that extra energy is going to go out as light somehow. So the energy of that fall, the energy of what that electron loses is actually what is emitted, is equal to what is emitted as a photon into our eyes, the detector. All right, so the sign of delta E, if the electron falls, negative. It is negative. So if we think about that, you know, think back to exothermic versus endothermic reactions. When delta H is negative, is heat released or is it absorbed? In an exothermic reaction, right? It's a negative delta H. Heat is released or is it absorbed into the reaction? Released. So what do we as the observers, right, the surroundings, we observe heat being emitted from a reaction. So it's the same idea here. When the electron loses energy, it's a negative change in internal energy. So what do we observe? We observe not heat, but light instead. So the sign here just tells us the direction of energy, again, just like all thermodynamics. So don't let the sign screw you up, all right? In all cases here, the energy involved with this transition still applies this equation E equals hc over lambda. So let's look at these examples. If n starts at 1, goes to 5, is the photon emitted or absorbed? Emitted or absorbed? 1 to 5. Absorbed. Just think to yourself, okay, we got an electron on the first rung. We want to bring it up to the 5th rung. We have to put energy into it to make it go up. All right, if it goes from 3 to 2, is a photon emitted or absorbed? Emitted. Cool. So it's a lot of these emission transitions is what results in the line spectrum for the hydrogen atom. That's what we're seeing. We're seeing 4 different transitions between different energy levels within there. All right, and so to kind of just like wrap things up again, kind of summarize stuff, this is the equation for the energy of one energy level. All right, but typically we use this equation to calculate the energy or change of energy of our atom between a transition, right? So note how you see N initial and N final here. That light is only involved when there's a transition happening between different energy levels. If an electron is staying on the same energy level, no light is emitted at all. And so how the energy of the atom is related here. All right, so this is energy of your atom. The energy of the photon that is emitted is always the absolute value of the energy of the atom, because this value can be negative when we're talking about emission, but the negative sign just tells you the direction of energy. The calculation is still the same, so don't let the negative sign scare you. When we calculate energy of the photon involved, it's always the absolute energy change of the atom. All right, and so to kind of just think about this again, if a hydrogen atom absorbs a photon, does N increase or decrease? Absorbs a photon. Increase, because you can just, think about a photon as just energy. All right, so that means the delta E of your atom is a positive number. Positive number, all right? And in both of these cases, E of your photon, the energy of your photon, equals the absolute value of the change of energy of your atom. Okay, and so if a hydrogen atom emits a photon, does N increase or decrease? Decrease, very good. So the energy of your atom is a negative sign, this case. And again, just telling you direction. So that means if we think about the transition between like N equals 1 and 2, the photon involved in that transition is the exact same energy. It's the exact same wavelength. It's just telling you, hey, is the photon being absorbed or is it being emitted in this case? And that's just a difference of sign. Okay, so we're going to do an example yet? Yes. Finally, okay. So let's do an example. Based on this energy diagram, we have A, B, and C transitions. Which pictures of light represent the A, B, C transitions? So take a minute, think about it. And did I give you hints? Yes, hint. These pictures of light differ by what quantity? Think about which wavelength has the most energy, which one has the least energy. So take a minute and get that, discuss that with people around you. All right, so 1, 2, and 3. What's being depicted here? Wavelength, frequency. Okay. I'm just going to say 1 is a short wavelength, while 3 is a long wavelength. So actually, let's just order them in terms of energy. Which picture has the most energy? 1. 1 has the most energy. Do we see that? Because you can think of it as the largest frequency if it's moving at the speed of light, or it has the shortest, peak to peak wavelength here. So it's the most energy. And then which one has the least amount of energy? 3 has the lowest energy. And then 2 is somewhere in the middle. So we think, okay, this is the photon that's involved with the transition. Which transition here has the most energy involved? Which transition has the most energy involved? C, A. So A is the largest drop. Okay, I don't want to be morbid, but what's going to hurt more if you fall from, 10 feet versus 1 foot? A larger drop is more energy released. All right, so A actually is the largest energy. Okay, so this is the largest energy, so that means 1 is going to be A, okay? And so the transition here, C, remember energy levels, they converge as they get closer. So we're looking at the transition, the energy difference between those higher energy levels. It's smaller, so that's a small energy involved. Small energy, so C would be number 3. So that's C, and then 2 is B. All right, so let's try another one. It's very similar. Okay, which of these electronic transitions for a hydrogen atom corresponds to the emission of a photon with the shortest wavelength? I'll get you started. Emission of a photon. This is what you should be thinking about. Does N increase or decrease during emission? Decrease. So we're going to look for decreases. So that eliminates half of them. Very good. Right? So we're looking for an N going down. So we can eliminate what? A and B. So we're just looking at C and D. So we want the shortest wavelength. That means in terms of energy, do we want a high energy or low energy? Short wavelength is a high energy. So we want the largest energy drop. So this question is tough because I didn't give you an energy diagram. So you have to draw it yourself. All right, so you draw it so the higher energy levels converge as you get higher, okay, like that. So this is N equals 1, 2, 3, 4, etc. Okay. All right, so I'm going to just draw these transitions. So N equals 4 to 2, so something like that, or 3 to 1, so there. So which energy transition results in more energy level transition is more energy? D. Yes. So I'm going to just point out real quick. If you didn't draw your energy diagram like this, if you drew it like this, where everything's equal, can you answer the question? No, you can't. So if you don't draw the energy level diagram correctly, you won't be able to answer it. Right? Because all the differences are kind of the same. They're all the same. All right. There we go. Okay, I have 2 minutes. Very good. All right. And then you can... So what's really great about questions like these is we can ask them a bunch of different ways. We can say, hey, what about the absorption of an electron with, the shortest energy? So we can just make little changes to the question, but they're all basically the same, right? So you can answer kind of these other questions related to this. You just pick different answers. All right. So we'll just end with this last calculation. So kind of tying it all together. Now we can actually calculate the wavelength of light or the energy of light involved in an electron transition of a hydrogen atom. So what is the wavelength of a photon emitted in nanometers when a hydrogen atom undergoes this transition? 4 to 2. So that's what we just did, right? We just did 4 to 2? No, we didn't. We did the other one. So we are looking for this, okay. We're looking for this transition, right? So we just plug in N equals 4 and n equals 2 into these equations. So we do 1 over 4 minus 1 over 16, minus 1 over 16. So what we get here in the parentheses when we do that calculation is 0.1875, and multiply that by this constant here outside of the parentheses. Okay, so just multiply those two numbers together, and we get that the change in energy of our atom is a negative number. So note here that we're multiplying it by a negative sign. So it's a negative number, but again, don't let that scare you. If it's a negative number, then that means is the atom losing energy or gaining energy? Losing, so that means is an electron being absorbed or is it being emitted? Emitted, and that's what we wanted to do. We want to see what is the wavelength of energy or the photon emitted. So this is the value that you get. So just take the absolute value here and plug that into the equation hc over lambda and calculate for lambda. That's it. That's it. So we already know this last part. So what we get is lambda is 4.86 times 10 to the negative 7 meters, or 486 nanometers. All right, so there we go. I'll see you on Friday.